Oftentimes when you're working a physics problem, you'll notice that the problem requires you to report the answer in terms of something like give the vector answer, or give the answer in terms of the full vector of the problem. And in this video, I want to show you what that means and how you would do that. The most common example I can think of like that, and there's going to be plenty, is where something's flying through the air like this, it's sort of whizzing along like this, and the problem say wants to know what is the velocity of the object just before it hits the ground. So say the ball is, say, right here, just about to hit the ground, and this is the v vector it has right as it is its impact. So what would you say about that v vector? Now intuitively we sort of drew the v vector on this dotted line here, but this is not sufficient for an answer. This is just some sketch here. But in particular for this v vector here, we like two things. We like the full mathematical and precise magnitude of the vector, and number two, we'd also like the direction of it. And we'd like numbers for these two things here. Analytical numbers. You can box in and say something like it's 13 meters per second at 27.5 degrees. Something like that. Very particular. Let me show you how to do it. So most often when you have a problem like this, let's just recast in terms of the Cartesian coordinate system so we can sort of get our heads straight on this. The velocity vector would be pointing straight up like this here if it was in this coordinate system. Now I realize I'm not working this problem. We'll come back to it in just a second here, but I just want to illustrate what's going on here. Often when you work a physics problem, you don't have this vector directly. That never sort of pops out of a problem directly, at least the way we analyze them in this class. But what you will always have, you'll always have the components here. You'll always have a v sub x like that, and you'll always have a v sub y like that. You can usually count on having these two things for sure the way we analyze problems here, because there's equations that deal with them, and you can just get those directly. So often, when they say give the vector answer, you won't have the velocity vector say as this thing lands, but you will have the two components, the x and y components. So how do you go between magnitude and direction and components? Well, let's just look at that now. The first one is probably the simplest here. The way you get the magnitude of the vector is you just look back at the right triangle here and go, oh, okay, the components, the x and y components, are the legs of the right triangle. Okay? And the magnitude can be found by using the Pythagorean theorem. So v is going to be the square root of vx squared plus vy squared. That's where the magnitude is going to come from. And you can always find the magnitude of the vector by using the Pythagorean theorem on the two legs. This will be the magnitude, and this number here that you get after you hit square root on your calculator will be the magnitude as needed by the problem. The second thing that you'll need here is the direction. The direction of the vector. Well, where's that going to come from? Again, look carefully back at the right triangle, and what you notice is that for the direction, you want an angle somewhere in there. Because you'd like to say something like it's 45 degrees or 37 degrees. You want something very specific you can say about this direction as demanded by the problem. If you look at the right triangle, we'll call it angle alpha right in there. Alpha is the angle between the x-axis and where the vector exists. And that would be a perfect angle to report for the direction. It could be 0 degrees or 10 degrees or 20 degrees, but you could say something like some angle alpha with respect to the positive x-axis. That would be a great way of doing it. If you look carefully at the right triangle, you'll notice then that the tangent of alpha is equal to vy over vx. Opposite over adjacent, the opposite side over the adjacent side, and there's the relation you need for alpha. So once again, just like the magnitude came from vx and vy, well, it looks like the direction is going to come from vx and vy also. So that's why those legs are so important. Those things that you calculate in the physics problems are so important for completing these things, because it often leads to the full answer you need, the magnitude and direction. One more step is required here. Alpha is actually going to be the inverse tangent of vy over vx, and that'll give you the angle directly. So those legs of a vector are incredibly important for getting these things to come out, like the magnitude and the angle. Now a bit of caution is needed here in interpreting this angle right here. You really need to look back at your drawing before you say with any absolute certainty about exactly what's going on, because here's another example here. Here's a Cartesian coordinate system, and say the vector is down like this. It's way over here. If I draw in the x and y components, which you're always able to do here, I'll say, well, here's say v sub x like that, and here's v sub y like that. Now if you look very carefully at this thing here, there's some signs going on. In particular, where would you draw your angle now? Well, there's a lot of places you can draw your angle. I'll put it, say, right in here. There's an alpha in there. And if you look carefully, the tangent is still what you'd use here. You'd still say in here that the tangent of alpha is the opposite over adjacent side. Is going to be vy over vx. Yes, that's still true. But now vx and vy will both have negative numbers, because vx here is going to be negative since it's pointing over this way. Vy is going to be negative because it's pointing down that way. And so you have a slightly different sign issue going on here for the tangent. But the bottom line is you just have to be careful about how you interpret this equation right here, because in this case here, alpha as drawn is definitely not with respect to the positive x-axis the way it is up here. You would say to the final answer, you'd say something like so many alpha degrees. You could say something like counterclockwise with respect to the negative x-axis, something like that. So I'll say also, let's just put a box around this thing here, and we'll just note also that you'll always be sort of like, let's just say, careful with the interpretation. Just don't blindly punch in your calculator and plug in a number, because you sort of have to adapt your angle and your tangent with the problem that you are working on in particular. So to conclude this video then, let's just report the initial problem here is how would you report, say, the angle of this final vector over here? Well, typically the magnitude, once again, will come from the legs just before this thing strikes the ground. You can see it'll have a Vy, which is going to be negative, and it'll have a Vx over here, which will be positive. So you'll often have those two components as a result of your analysis of the problem, which is an entirely different issue that we're not addressing right here. Let me just erase some of this here to give us a little bit of room here like that. And so that original problem that I mentioned is there stated. How would you report the magnitude and direction? Well, the magnitude, once again, the velocity which this thing will slam into the ground, will once again come from the square root of Vx squared plus Vy squared. That's where that magnitude is going to come from. You can get that very simply. Again, often Vx and Vy will be at hand if you've properly worked a projectile motion problem like this. Where would the direction come from? Well, a variety of ways. I'll go ahead and draw a little alpha right in here. That's where my alpha would be. And if I look carefully at the right triangle formed between the legs here of the projectiles Vx and Vy, again, there's leg 1, there's leg 2, there's the vector here. It does look like the tangent of alpha is opposite Vy over Vx. So again, if I have Vy and Vx to get the magnitude over here, I should also have them available to calculate the tangent. And so this angle here would be reported sort of in an interesting way. We have to say sort of like alpha degrees, and now we have to say, well, with respect to what? Looks like to me, if I did something like this, I could say alpha degrees, I would say with respect to, we'd say something like maybe clockwise up from the negative x-axis. Something like that would probably work. Where did I get all that from? Well, I go back to where that vector actually exists. It sort of exists down here like this. Here's the vector here. Here's the x-axis. Here's negative x over here. So the way I've drawn that alpha in there, it looks like I am coming up clockwise relative to the negative x-axis. That's how I'm reporting alpha. So again, I'll put a little call out around this thing here, and I'll say once again, like we included in the last part of the video, be careful here, because that angle is always subject to some interpretation, which is going to be in general different for every problem. Sometimes it'll be positive x, sometimes it'll be positive y, sometimes it'll be negative x, whatever. So you also have to interpret that angle, and I'll even just sort of leave the video with one last thing for you to think about in terms of this interpretation idea of the angle here. Suppose I didn't put alpha right here. Suppose I wanted to put my alpha right here. That's a perfectly legitimate angle to use in interpreting this here. So we'll look at it and go, okay, some things are going to change about this now. If I choose to put the angle up there, watch what will happen. Even the tangent will come out to be a bit different here. Again, you have to be careful with the interpretation. The magnitude will be the same. You can still get that using the Pythagorean theorem. But if I look at the purple alpha now, which is perfectly valid, looks like tangent alpha then is opposite over adjacent. It's Vx over Vy. And you have to put a couple exclamation points like over this, because it's not even Vy over Vx anymore like it was in all the cases I've done so far. Again, this is the interpretation that you have to be careful with in these problems in interpreting what angle is and what direction. So in this case here, when I finally get my alpha, I'll report something like alpha degrees. And what am I going to put? Let's see. With respect to, well, it's not even clear. Let's get it all drawn on there. Let's draw our Cartesian coordinate system on there like this and like this. That's the positive x-axis. This is the negative y-axis. So I'd say with respect to, looks like I'm moving counterclockwise with respect to negative y. That's a very unambiguous way of noting this thing here, because alpha sits in here, and it looks like I have to come up to get that angle. To sweep out where the vector is, I'd come up counterclockwise with respect to the negative y-axis in order to get that angle. So, bottom line here is you have a way of reporting the magnitude. Number 2, you have a way of reporting the direction, and the direction usually comes from some inverse tangent. 2 steps. 1, an inverse tangent. Number 2, you always have to go back and interpret alpha, or the angle, in order to get everything to work out right, because you must report your vectors properly.